speaker of today, Ferenc Krausz. Ferenc got his undergraduate degree in Hungary from the Technical University of Budapest and then at Adverse University, moved on to the Technical University of Vienna, where he did his PhD. And actually, to put this in perspective, he got his undergraduate degree in theoretical physics, but then later moved into laser physics. And he stayed at the Technical University of Vienna for quite some time, did his habilitation there, became assistant, and then very, very soon after, full professor. And you have to tell me later how you did that, but that's great. And then he actually, what I find most remarkable is that Ferenc, in fact, has multiple inventions that paved sort of his way. One of them is dielectric coatings that enable to produce extremely short pulses of light, and I'm sure he will cover that to some extent. And then he was using these technological advances that he developed within his group to produce in 2001, the paper was published in 2001, isolated attosecond pulses with his team. And the Nature publication from that time made great waves because essentially it was the birth of attosecond physics. And the field since then has proliferated. So attosecond science started as just a curiosity of how to produce attosecond pulses, but soon after, attosecond science was born, trying to utilize these pulses to understand the world of electrons. Again, I will leave this up to Ferenc to explain in a bit more detail. I've gotten to know Ferenc when he moved to the Max Planck Institute of Quantum Optics and the LMU in Munich in about 2003 and 2004. And I've been working there with him until I moved here. So for, I think, almost 18 years. So Ferenc is has been my mentor for a long time. It's my great pleasure, actually, that he's here and I'm able to introduce him. And Ferenc has gotten many awards, among them the King Faisal Prize in 2013, and then the Wolf Prize in 2022, and most notably, the Nobel Prize in Physics last year for his attosecond pulse metrology, so for starting the field of attosecond physics. So thank you, Ferenc, for visiting us and giving us the pleasure of your presence, and please take it away.
Thank you, Matthias. Thank you for this very kind introduction, as well as in particular for the invitation and for having me here. It's somehow a strange feeling because this is the very first time in my life that I visit this place, which is an absolute shame, and I feel deeply ashamed. But I have to confess you that I somehow yet feel here like being at home. Having met just over the past few hours so many good friends and having had great discussions, and having been impressed just incredibly. And how you define here new frontiers in our beloved field, attosecond science. I think no one could possibly foresee, no one even dared to dream of only 10, 20 years ago. So I would really like to start with congratulating you on having created attosecond metrology 3.0. It's an enormous achievement, and it's just hard to imagine what this will open up the door to. But obviously, the only thing we can be sure about is that we cannot possibly foresee what this will enable us, you in the first place, but of course, given that this is a user facility through you, thanks to you, to the whole world, enabling entirely new applications, which we cannot precisely foresee today. So I have to confess that I may disappoint some of you, particularly. Sorry, you don't hear me, or? Yeah, it's better now. Let's see. Just try to get it closer. Yes. Is it better now? So whilst you have created attosecond methodology 3.0, I'm now kind of bringing you back in time and would like to share with you how attosecond methodology 1.0 and later on 2.0 emerged and more recently opened up some perspectives for possibly even real-world applications. With my lecture, I would like to deliver an example for what I believe is an eternal truth of Max Planck. The more delicate details are by which we can follow nature on any path, the richer and more lasting will the gains be that we can draw from this perception. In my example, the delicate details will be electronic motions, obviously, in tiniest dimensions in space and time. And one of the hopefully lasting gains will be the cost-effective probing of human health. More specifically, I will how the new discipline of attosecond physics opens the door to the world of subatomic motions, of course, subatomic motions of electrons, and how these motions can actually be initiated, controlled, and captured by light. And I would also like to address how these motions can actually be exploited to control light, providing thereby the tools for the new discipline, attosecond physics. The interaction of electrons with light plays a pivotal role in advancing existing as well as spawning new technologies. I will present two examples, but it's quite likely that others are yet to come and possibly even more important ones. The more precisely we are able to control electrons, light, and their interactions, the richer and the more lasting the gains will be that we can draw from this ability. This would be my version of Max Planck's eternal truth for you to take with you home today. Before we immerse in the world of electrons and light waves, it is worth remembering that these entities, electrons as a wave, electrons as a carrier of the elementary charge, light is an electromagnetic wave. These entities did not exist in the repository of human knowledge until less than 150 years ago. We just project this on the time scale of the history of the Homo sapiens. This is quite a short period of time. Less than 150 years ago, we just didn't know what electrons are and what is the nature of light. So it's always important to remember that we are standing on the shoulders of giants. Groundbreaking discoveries of the late 19th and early 20th century laid the foundations of all the technological advances that harness electrons, light, and their interactions. For instance, processing and transmitting information. It all began with Faraday's experiments on electrolysis, which together with independent hints that elementary substances are composed of atoms led to the conclusion, and this conclusion was drawn by no one else than Hermann Helmholtz, led to the conclusion that electricity must also be divided into elementary portions. After mounting evidence by Philip Lenard and others, it was a series of experiments by Joseph Thomson that shed light on the nature of carriers of the elementary portions of electric charge. subatomic particles called electrons, negatively charged by convention, orders of magnitude lighter than the hydrogen atom. In parallel, Maxwell's theory, Hertz and Röntgen's experiments revealed that radio waves, infrared and visible light, just as X-rays, are all different manifestations of the same thing, electromagnetic waves. But why doesn't this subatomic particle, the electron, charge negatively, which is supposed to somehow orbit around the positively charged nucleus? Why doesn't it actually propel into the positively charged nucleus, as it should do actually by the laws of classical physics? Why does it actually fill a sphere which is about 10,000 times larger in diameter than the diameter of the nucleus, instead of spiraling into the nucleus? The electron's wave nature and the linear relationship between its wave number and momentum, as postulated by de Broglie, delivers a very simple explanation. We don't even need to deal with complicated things like Schrödinger equation and all the other subtleties of quantum mechanics. If electron is a wave, the wave number of which is proportional to the momentum of the particle, if we want to make this wave ever smaller, to be ever closer to the nucleus, this implies ever bigger wave numbers. Ever bigger wave numbers imply ever bigger momentum, which of course counteracts to compressing the particle in ever smaller volume in space. So qualitatively, we immediately understand, based on these two postulates of de Broglie, that why an atom is much bigger than the nucleus. Obviously, Erwin Schrödinger was so much inspired by this that he just a few years later postulated his famous equation for the electron's wave function. And I would say equally importantly, but often not appropriately appreciated, it was the probability interpretation of the wave function by Max Born, who, with quite some delay, earned the well-deserved prize for it, resolved basically this the paradox between the electron as an immeasurably small particle, at least up to now, immeasurably small, with immeasurably small extension, and the finite size of the wave function, represented actually by the modulus square of this wave function, as depicted here by the green cloud for the prototypical ground state of an electron, the ground state of the hydrogen atom. The wave mechanics of Schrödinger and Born revealed that subatomic motion can only emerge by exciting an electron from its ground state to a superposition of stationary states. The resultant temporal variation of the electron's probability density constitutes the closest possible analogy to classical motion, exemplified here by the dipole oscillations of the 1s2p superposition state in the hydrogen atom. 75 years after subatomic motion had been described in theory, it could be captured in real time. Two major discoveries at the middle of this 75-year time span have been decisive for the emergence of this technical capability. The first is, of course, as you all know, the laser demonstrated by Mayman, utilizing the concept of stimulated emission of radiation, discovered by Towns, Prokhorov, and Basov, and perhaps less known to all of us, the theoretical prediction of Keldysh that ionization by electron tunneling may occur with substantial probability within the half-wave period of a sufficiently strong and sufficiently slowly varying, slowly oscillating optical field. Based on these two major milestones occurring in 1960 and 1964, which by coincidence are two dates which are completely symmetric to my birthday, several advances paved the way to the birth of attosecond science, one of them being the generation of intense near-infrared laser pulses carrying a substantial fraction of its of their energy in a single oscillation cycle, which were first demonstrated in Vienna in the mid-90s in the framework of a multilateral scientific collaboration, as you see here. Again, by drawing on concepts developed by others, like the Nobel Prize-winning concept of chirp pulse amplification by Gerard Mourou and Donna Strickland. I have to disappoint Matthias. I have to apologize, but I'm not going to talk about any details how to generate this. This would have covered, of course, the chirp mirrors, but I think it's perhaps more exciting to see what we can do with these guys. Just for brevity, I will briefly refer these pulses as single cycle laser pulses and waveforms in the remainder of my talk. Exposing noble gas atoms to such a single cycle laser field creates ideal prerequisites for the optical field induced tunneling predicted by Keldysh decades before. Here you see what is supposed to happen according to Keldysh. So the green depicts just let's be simple. Let's look at the most weakly bound electron, and it's basically the kind of wave function of this most weakly bound electron. For the sake of simplicity, if you kind of disagree that this is too strongly simplified, just think of a hydrogen atom. Then there is just one electron, and then this is perfectly right. This is also a good, this single electron approximation turns out to be a good approximation, even in atoms containing a lot more electrons. There is always one electron which can be ripped off most easily, and that's this electron here. So now let's see what happens if a so-called cosine shaped waveform in which the central half cycle is most intense and is really the peak of the pulse, and then there are maybe two somewhat weaker half cycles earlier and later, and then a little bit of something beyond that. So such a cosine shaped waveform impinges on such an atom. What happens then is that as you will see, if the field is strong enough, then on the peak of the central half cycle, the Coulomb potential that binds this electron to the nucleus is suppressed so far that the electron can tunnel through this narrowed barrier, which is narrowed, of course, just for a very, very short while. What happens afterwards is, in a linearly polarized laser field, that the strong electric field drives the electron away from the atom along a straighter trajectory. After several nanometer excursion, the electron is pulled back to the vicinity of its parent ion, where it re-encounters the bound state portion of the wave function of the same electron. This is deeply quantum mechanical, right? That this particle, the electron, can be split up, although in reality the electron can never be split up because it's an elementary particle to the best of our knowledge. But nevertheless, its wave function can be split up, and part of its wave function can stay bound, which indeed happens in most practical cases, and just a tiny fraction of its wave function tunnels through the barrier, does this excursion, comes back, and now the two portions can overlap as this electron is returning back in the next half cycle of the strong field. So now let's see the full movie. What happens? So first, the electron with a certain probability is detached. It goes away within a quarter of a cycle after the detachment, and then in the other half cycle pulls it back, and it interferes with the bound state fraction of the wave function of the same electron, and this interference results in very fast dipole oscillations as this quasi-free electron flies through the nucleus and through the parent-ion. And these fast oscillations form basically a fast oscillating dipole, which of course emits light, and the faster the dipole oscillates, the higher the frequency, obviously, of the emitted light. So simple Newtonian and mechanics and Maxwellian electrodynamics provide insight into how tunneling ionization may imply the emission of XUV light. The only thing that is really quantum mechanical here is the tunneling and the postulate that basically one and the same particle can split up, and basically the two parts of the same particle in the form of the two portions of its wave function can come to interference with each other. What is also pretty obvious from this simple picture is that the duration of this burst must be very short, and it's highly likely that it's substantially shorter than the oscillation cycle of the driving field, because the whole process, tunneling, excursion in the field, recollision, this whole process occurs within less than one full cycle, roughly 2/3, 3/4 of the cycle. And the cycle is in the near infrared, maybe a couple of femtoseconds. So it's very, very likely that this guy here is something in the order of 1 femtosecond, or possibly even shorter. And that's what we, of course, tried to measure in the 90s, but it was a long struggle. So what was pretty easy was to actually generate this XUV light. So that's what is indicated by this violet beam. Just focus this single cycle light into a tube with two small holes in it, which define the interaction region. Within this tube, a couple of 100 millibar of neon, and already this XUV light comes out at the other end. So this was the easy part. From here, to figure out what the time structure of this guy is, which is delivered in this pencil-like beam, this took us 5 years, and many frustration. But eventually, the message is frustration pays off. Yeah, if we are sufficiently willing to survive frustration, then eventually we will be rewarded. And this shows you how the reward came. So basically, we focus these two beams into a second gas jet with a so-called two-component mirror. The internal part focus the XUV light, the external one, the single cycle laser field. And as you see, the internal mirror, actually an XUV molybdenum silicon multi-layer mirror, also served as a bandpass filter, isolating the highest photon energies in this very, very broad high order harmonic spectrum. And you see that actually the portion which was isolated, which was filtered out, actually doesn't even exhibit any harmonic structure. So here the harmonics coalesce, which was actually a first indication that the time structure doesn't really seem to exhibit a periodic structure, which is the time domain origin of the harmonic structure in the spectral domain. So this was a good sign, but of course this was still not a direct information about the temporal duration. But a cross correlation measurement between the strong field and the XUV pulse in the second gas jet already delivered a first hint that the duration of this radiation isolated with this XUV mirror in the cutoff region of the harmonic spectrum was at least less than 1 femtosecond, actually less than even 650 attoseconds. That's what we set as an upper limit. We couldn't be much preciser than that at that time, because the electric field waveform in the single cycle pulse, which was used for the generation of the XUV light and afterwards for its measurement in the second gas jet, was not precisely controlled yet. We could at that time only control the envelope of the pulse, duration, everything, but not exactly how the oscillation occurred underneath the envelope, which was due to the lack of control of the so-called carrier envelope phase, which actually determines the relative phase of the carrier underneath the envelope. This control, before I come to that, the heroes of the experiment are Michael Henschel and Reinhard Kimberger. And here you see actually the internal part of this chamber, which we are trying to put together now. The Nobel Prize Museum would be very interested to exhibit this. And this is a true challenge, because I have to tell you that this has been cannibalized after the experiment. So the only thing that really survived was the vacuum chamber. So we now try to kind of put it together as good as we can. Anyway, just to go on, a couple of years later, laser pulses with precisely controlled waveform enabled indeed highly reproducible generation of isolated attosecond pulses, as well as their precision metrology by implementing Paul Corkum's concept of what we call light field driven streak camera. He preferred to call this attosecond streak camera. What happens here is the XUV pulse again, we'll see in a moment, the XUV pulse again hits the atoms, the krypton atoms, and releases photoelectrons. This time we measure the flight time of those photoelectrons which are ejected parallel to the linearly polarized single cycle laser field. This is what will, as you see in a moment, actually streak these photoelectrons energy distribution, momentum distribution, and that the result of that will deliver the information about the temporal structures. And that's what you will see now in a moment. Depending on the moment of release of the photoelectrons, the electrons are accelerated or decelerated by the laser field. This is the delta P, can be either negative or positive. And this is what actually streaks the electrons temporal distribution, or the XUV pulses temporal distribution, and maps this temporal profile of the XUV pulse to final momentum distribution of photoelectrons, here depicted by the green distribution. Recording this XUV-induced and laser-streaked photoelectron spectrum as a function of delay results in a spectrogram that allows complete retrieval of both the laser waveform and the complex amplitude of the attosecond XUV pulse. These experiments demonstrate how control actually enables observation, this time on an attosecond time scale. and render the basic tools, the attosecond varying light force and attosecond duration XUV light available for real-time observation and control of electron light phenomena. With these tools in place, we can set out to perform attosecond spectroscopy and attosecond time-resolved spectroscopy, of course. And we have done a number of such experiments over the past something like 15 to 20 years since these tools became available. I would just like to pick one as an example, which is in some sense my favorite one, because it's so close to what I presented you at the very beginning, how we understand actually subatomic motion. Let's see what happens if an atom is exposed to the single cycle light. We have discussed before that what happens is that the strong field will rip off the most weakly bound electron with some probability via optical tunneling ionization. And that's what we are going to look at in a moment. Again, essentially with the same setup, but just slightly modified or actually extended by adding an XUV spectrometer behind the sample. And in addition to still looking also at the photoelectrons, if we wish, the photoelectron spectrometer disappeared, but in reality, in the experiment, of course, it's still in place. So we can do both. We can measure the photoelectron spectra to do streaking, to measure all the time the temporal characteristics of our attosecond pulse, as well as the single cycle laser waveform. But here I would like to focus your attention to the XUV spectrometer, which captures the spectrum, the photon energy spectrum of the XUV probe pulse transmitted through the gas jet, which is being ionized by the single cycle laser field. Here we see how this spectrum looks like if the attosecond XUV probe precedes the ionizing pulse. Then, of course, the XUV light doesn't know that ionization even happened because the XUV pulse traversed the sample first. But we can, of course, delay the XUV pulse such that it comes after ionization, and then all of a sudden, these absorption lines, beautifully, cleanly measurable absorption lines show up, and the depth of these absorption lines scale with the number of ions generated by the single cycle laser field, because these absorption lines show up only in the ions. They don't show up in the neutral atoms. So obviously, if we now measure just the depth, just how these lines change as we change the delay between the ionizing single cycle field and the attosecond probe pulse, we can probe processes like the tunneling ionization itself. And that's what is summarized here, basically the results from such a measurement. So we just do it in slow motion replay so that our eyes are able to follow it. And you see how the ion population builds up. Indeed, as we actually expected, largely within the central half cycle of the single cycle pulse. And this black line, it is not just a sketch, but this is the measured instantaneous intensity of the ionizing field. We can measure it because the streak camera is still in place, right? So whilst this measurement is being done with the XUV spectrometer, in the same setup, the streak camera measures the properties of the single cycle laser field and the attosecond XUV probe. So two attosecond measurements simultaneously, and that gives the information not just about how the laser field looks like, but also how the relative timing of the growth of the ion population lies with respect to the pulse. That this growth in ion population is not happening here or here, but exactly at the center, right? That's what we also draw from the simultaneous attosecond streaking measurement. So it's truly powerful to do two measurements at the same time. And I was very impressed to see that actually you plan to do the same thing with your beautiful, actually even more powerful, to be honest, circularly polarized streaking. Truly impressive instrument, and combining basically the information about the direction of the photoelectrons with their energy distribution. Wow, great, really great. So just remember slow motion replay with temporal magnification of 10 to the 15. I'll come back to this in a moment, but let's now just take a close look at the comparison of the result of the measurement and the prediction of the famous theory of Keldysh. Actually, this is already an improved theory by Amosov, Delone, and Krajinov, ADK, who actually improved the theory of Keldysh quite a bit. And what we see here is that that actually the theory predicts a faster rise of the ion population, a faster electron tunneling than we measure experimentally. So obviously, what we see here for the first time, and there is no other way to see this, but attosecond spectroscopy is non-adiabatic optical field-induced tunneling. The electron tunneling current does not adiabatically follow the variation of the strong field. If it would, then it should grow like the green line. This is the quasi-static theory of Keldysh and ADK, but is a bit slower. So obviously we see first signatures of adiabicity. This near-infrared laser field in 750 nanometer carrier wavelength is slightly too fast already for adiabatic tunneling. What is also important to mention that actually the electron is not liberated from just one state, but there are two states on the 4p 4p shell subshell, which are spin orbit split, and the electron can be liberated from both states with reasonably comparable probability, as you see here. And as you remember, we discussed it at the beginning. Creation of a superposition state gives rise to motion. And indeed, the recorded transient absorption spectra exhibit a periodic variation with increasing delay of the XUV probe. This is the delay axis, and this is the spectral distribution of the recorded transient absorption spectra. These are the dips, right? These are the dips that I showed you on the first slide, which starts actually this discussion. And this, you see how this varies at later delays. After the ionization is done and the ion is left behind with this hole in its side, but the hole is in a superposition state. And thanks to this superposition, obviously there is a breathing here, and its 6 femtosecond period corresponds exactly to, not surprisingly, to the 0.7 electron volt energy separation of the two spin orbit levels. To develop the film from these transient absorption spectra captured with 150 attosecond exposure, the photographer's job is taken over by theorists modeling the interaction. A good agreement between theory and the experiment allows to retrieve the attosecond snapshots of the whole density distribution, as well as actually the initial value of the quantum phase, which actually determines that initially in the moment of ionization, the hole looks like this and not like this, which is perhaps also to some extent intuitively expected, given that this is the polarization direction of the laser. So basically the hole that emerges in the first moment of ionization is aligned along the laser field. And from that, again, we can reconstruct the motion in slow motion replay. When rendering these motions accessible to human observation, attosecond spectroscopy furnishes us with a temporal magnifying power of 10 to the 15, which happens to be roughly equivalent to the combined magnifying power of a space telescope and an electron microscope altogether. Now, this sounds really, really impressive, right? But I have to disappoint you. This doesn't mean anything much than actually our eyes are much poorer detectors in time than in space, right? So to actually see atomic structure, we need a magnification of 10 to the 8 in space, but we need magnification of 10 to the 15 in time, right? Just very poor detectors, these guys here, temporarily, but fortunately, we have attosecond technology, so that helps. To quote Eva Olson, we can now open the door to the world of electrons. Attosecond physics gives us the opportunity to understand mechanisms that are governed by electrons. The next step will be utilizing them. Easy to say, but in order to be able to tackle real world challenges, really, attosecond technology, so far relying on these guys and these complex vacuum systems, must become simpler and more powerful. So far, it was attosecond technology 1.0, and now, new chapter, we start talking about attosecond metrology 2.0. And I'm not going to speak about chapter 3. That's your business, right? This attosecond metrology 2.0 was recently enabled by single cycle light, owing to its ability to realize the same process in wide gap solids that we have just studied in atoms, optical field induced electron tunneling. So we are back again, 1964. Keldysh described this process as well. He described ionization both in atoms as well as in wide gap solids. And he predicted that it is supposed to happen in wide gap solids as well, but it took something like more than 30 years to realize the experimental conditions that really allowed this to happen. And these experimental conditions are confining of the energy of light into one single cycle. Why is that important? Not just important, indispensable. Why is this indispensable? Because no solid matter could otherwise survive the required critical field strength of about 2 volts per angstrom for a wide gap solid. This 2 volts per angstrom realizes for the experts Keldysh parameter just below 1 in a wide gap solid like quartz with about 10 eV band gap. Only by confining these field strengths to the time scale of a single wave cycle can irreversible breakdown in wide gap solids be avoided. Tunneling is then largely confined to the central half cycle of a cosine shaped waveform. So in the same way, we expect, at least that's what theory predicts, and we'll see in a moment whether this is true. Again, we would expect that the actual liberation of electrons from the valence band here, we should rather say actually promotion of the electrons from the valence band to the conduction band. This promotion, this injection of carriers into the conduction band again is expected to be confined largely to the central half cycle. If so, as we will see in a moment, sub-femtosecond carrier injection can replace sub-femtosecond XUV light and obviate the need for complex vacuum systems for a class of applications. Highly relevant for advancing electronics. The control and probing of valence and conduction band carrier dynamics on attosecond, femtosecond scale. In a primary step, subcycle carrier injection is used for optical field sampling. By implementing it in a small volume between two electrodes, where the laser field, where the test laser field depicted in blue separates the injected carriers, the carriers that are injected by tunnel ionization at the center of the injection field, of the injection pulse, right? Carrier injection is depicted by this green pulse. So the carriers, the electrons in the holes are then pulled away, pulled apart by the test field to be measured, by the blue field. The injection field is polarized parallel to the electrodes to minimize the influence of on the macroscopic dipole formed by the electron hole pairs. The strength of this dipole is mainly determined by the drift momentum delta P, which is acquired from the test field. And this can be measured in the external circuit by just a current, basically by using an electrometer. The resultant current is then proportional to nothing else but the vector potential of the test field to be measured. So basically, the final result, in this case, the current is very similar to what we have in streaking. In streaking, it is the momentum shift that is proportional to the vector potential. Here, it is the current, right? The number of electrons that are flowing through this electrometer. And here you see, hopefully you see it, yes. Here you see this number of electrons flowing through the electrometer as a function of delay of the injection field with respect to the test field. And a benchmarking measurement using attosecond streaking reveals that obviously the new method, which we refer to as non-linear photoconductive sampling, NPS, also obviously is able to measure these field oscillations, and actually it can do quite a bit more. Meanwhile, the technique has proven its capacity to sample actually deep UV fields beyond 1.5 petahertz. Actually, these pulses are being generated by a simple hollow core fiber and are even able to spawn sub-femtosecond light. In this particular case, it was just slightly below 1 femtosecond, but Nick Karpowitz and Amelie Heinzelling have meanwhile generated sub 500 attosecond pulses out of this system. The thing that I want to emphasize for you, that the methodology is able to actually sample now fields up to frequencies in the deep UV with a temporal resolution better than 200 attoseconds. Light fields, and this without any vacuum. Well, yeah, I should say, of course, if you go to the deep UV, you need vacuum, but for another reason. Obviously, it would be absorbed in air, but otherwise, the technique itself doesn't rely on vacuum, as opposed to technologies based on XUV pulses. So light field sampling provides a new probe for attosecond phenomena. The electric field of light from the infrared to the ultraviolet directly probes the arguably most fundamental consequence of any light-matter interaction, which is nothing else but the displacement of electronic charge density, briefly polarization. It is imprinted in the electric field transmitted through the sample. This green curve is the induced polarization. Referencing this transmitted field to the input field allows for a thin sample unambiguous retrieval of the induced polarization depicted by the green line. Along with its driving field, this polarization determines the instantaneous energy flow from the light field into matter and vice versa. By integrating this energy transfer rates over time, from a moment just before the pulse arrives in the sample, yields the energy transferred from the laser field to the electrons within a unit volume. And that's what we plot here for two different types of materials. For an insulator with a large gap, in this particular case for near-infrared light, 6 photon band gap quartz, and in the prototypical smaller gap material, silicon, in this particular case, 2 photons are needed to overcome its band gap. For the highest field strength, which were limited by breakdown, so a little higher field in both materials would cause optical damage. For the highest field strength, as you see in both materials, energy transfer is irreversible obviously due to multiphoton induced transitions. These created a population, and this population survived the laser field. So the laser field could not reverse the energy that has been transferred from the laser field to the material. By the way, I would like to draw your attention on the y-axis. This is not just, as an exception, not just arbitrary units. This is electron volt per nanometers cubed, right? We quantitatively measure by this technique the amount of energy that is being transferred from the oscillating electric field to the material per unit volume, per unit time, with attosecond resolution. For decreasing field strength, what is very conspicuous that in the wide gap material, we very rapidly move into a completely new regime where the energy transfer becomes completely reversible. This is the yellow line on the left-hand side. So the field first transfers energy and then gets it completely back. And after the field, after the pulse is gone, the transferred energy is back to zero again. This is wonderful because this opens the door for dissipation-free signal processing. This is a nonlinearity here, still a nonlinear interaction, actually the optical Kerr effect. Thank you. This is obviously suitable for or a good basis for dissipation-free signal processing. These studies showcase how real-time access to the light electron energy transfer explores optimum conditions for ultra-fast optoelectronic signal manipulation. Given that I'm running short in time, I would perhaps skip a few slides and just move ahead to the last part of my talk, because I would really like to share in the remaining few minutes the application that is closest to my heart. But before I come to that, I'd like to draw your attention how actually the measurement of this polarization response uncovers the scale of the displacement of valence electron charge density, in this case in quartz. Remarkably, if you read the scale on the y-axis on the right-hand side, this displacement is of the order of just a fraction of a picometer, a distance smaller than 1/1000th of the diameter of an atom. And yet, such a subatomic motion is not only measurable, apparently, but may also serve as a basis for future petahertz rate electronics. Attosecond probing of this picometer or even sub-picometer scale electronic motion is not only relevant for advancing electronics to its ultimate limits, but the same technical capability also provides access to minuscule changes of the molecular composition of human blood, in our particular case, human blood plasma, which is known to be a sensitive indicator of health disease transitions. To sense these transitions, we propose, instead of searching for individual biomarkers, as a multi-billion scale industry is doing, accessing the global molecular landscape via field-resolved spectroscopy. We expose human blood plasma to a single-cycle infrared laser pulse, which coherently excites molecular vibrations within its spectral band. The vibrating molecules, in turn, radiate coherent infrared waves in the wake of the excitation, as you see here. This resultant signal is characteristic of the molecular composition of the sample. We capture this, what we call electric field molecular fingerprint with highly sensitive electro-optic sampling. This fingerprint signal is expected to change whenever emerging abnormalities change the sample's molecular composition, which we actually recently managed to verify for several chronic conditions, such as different types of cancer, as well as cardiovascular and some metabolic disorders. I just would like to share with you one single prominent example. Here we compared 470 samples of lung cancer patients with the same number of samples of reference individuals free from cancer, briefly controls. With the controls carefully matched regarding the distribution of the subject's age and other parameters. These are the electric field molecular fingerprints of all samples. On this scale, we see little differences between the individual signals, but zooming in, for instance, some 1000 femtoseconds after the excitation peak, where molecular emission obviously dominates over the excitation, clear differences between the two cohorts come to light. We can quantitatively analyze these differences, for instance, in terms of the gaps between adjacent zero crossings of the oscillatory signal, briefly half-cycle gaps. Here we show the mean and the standard deviation of the half-cycle spectroscopic markers, in this case more than 350 of them, evaluated from the fingerprints of stage 1 to stage 4 lung cancer, from the fingerprints of their controls, and most importantly, the differences between the two cohorts, brought it here, with respect to the mean of the controls. So basically, what you see here is very reminiscent of the upregulation and downregulation, for instance, of some analytes, some proteins, some lipids, or metabolites in the sample. Potentially, these guys here, the shift in the zero crossings of the oscillating electric field of the order of a few tenths to typically a few hundreds of attoseconds carries similar information about changes in the molecular composition of blood. Their magnitudes relative to the spread of the controls is referred to the effect size. You see it in the right upper corner, which in this case has been averaged over all 350 markers for stage 1 and 2 bunched together. This is yellow. Stage 3 and stage 4 non-small cell lung cancer. It is increasing for disease progression, as it should, if the differences between the case and control signals are indeed due to the disease. So physicists might tend to say this is a smoking gun, but I should tell you that that you shouldn't use this terminology in the presence of life scientists. They don't like it. The efficiency with which a well-trained algorithm is capable of distinguishing cases from controls critically depends on this effect size for obvious reasons. The effect size and hence the classification efficiency of the trained algorithm can be improved by two ways. Either by increasing the disease-induced signal. Well, I mean, we have little influence on the disease, and then the signal that induces, we may try to improve the sensitivity of our instrument, of course, but that may take long. What may work much faster by reducing the spread of controls. The spread of controls. I'm coming back to that in a second. The cancer-induced signal increases for progressing stages, as we see from this effect size. And here you see actually the classification efficiency of the trained algorithm for stage 1, stage 2, and stage 3, basically the early stages of lung cancer, which is extremely important because here you can save. Your life can be at least prolonged by many years if you are captured here. If you are captured at stage 4, then you have 6 to 12 months to live. Yeah? So that's quite important to capture the disease here. Yeah? But this is promising, but it's not all yet, because 1 minute in that time. Because I just emphasized that the effect size, which controls this classification efficiency, could potentially be increased by reducing the spread of references for obvious reasons. But how to, in this study, basically the references have been different healthy individuals, and they have a broad spread. But it turns out, if we could use another type of references, if we could use references from you, yourself, by having collected your samples years before you have contracted the disease, the spread of your own references is by almost a factor of 3, 2.5 to 3 smaller. We have evaluated this from a big study that we have rolled out in Hungary with 15,000 participants, that this spread within the person is by a factor of at least 2.5 smaller than in a healthy population. And if we now simulate how our algorithm would perform to recognize lung cancer stage 1, stage 2, stage 3 with the disease-induced signal that we have captured with our current instrument, we would end up being here, right? Stage 1 above 90%, stage 2 above 95%, stage 3 above 95%. There is no biomarker even in sight that would even come close to this, right? We would just need to persuade everyone to come for a blood test once a year, just a few minutes of your time. But before that, maybe persuade the healthcare systems to invest some funding into this. And that's basically what we are trying to do for good reasons. Every year, 70 million people under the age of 70 die of these 4 types of non-communicable diseases: cancer, diabetes, cardiovascular, and chronic respiratory diseases. 86% of them in low and middle income countries. We could save year by year 17 million lives if we would have a cost-effective method to monitor human health. And that's why I defined for myself and for my group at AttoWorld the overriding questions that we would like to pursue in the years to come. Can the molecular composition of human blood provide sufficiently comprehensive information to serve as a basis for population health screening? And can electric field molecular fingerprints make a contribution to accessing this information? That's what we are. That's what we are after in the years to come. And whilst trying to be after this, we're also trying to maintain the hopes of those who are already dreaming of joining in, as you see. this is a single cycle pulse here, right? I mean, a few more electrons around, but that makes the game even more exciting. This is Vladislav from Lyceum number 10 in Marhanets in Ukraine, not somewhere in Ukraine, but just a few miles away from the front line, where this guy is not allowed to go to school because there's constant shelling, right? We are supporting him, among many others, with the donations of that our organization Science for People is able to collect, because I think just as all other children anywhere else, they deserve a chance to realize their dreams, and they have dreams, as you see here. Please support us to allow us to extend our support to as many needy children as possible in war-torn Ukraine. We badly need all of them to carry on once our time comes to an end. Thank you.
All right, what a wonderful presentation. And we have plenty of time for questions. So please raise your hand. And then once we're done with the audience here, there's 1 or 2 questions online. So go ahead, don't be shy. Since nobody's asking a question here, maybe I can start. What kind of treatment do you need to perform to the blood cells to be able to perform this kind of measurement with attosecond technology?
Thank you, very good question. It's actually very, very simple. It's part of the daily routine in laboratory medicine practices, just a simple, very simple blood draw. The only key thing is that we have to centrifuge the sample within ideally less than 1 hour after the blood draw, and put it in a freezer at -80 degrees at least. Ideally more than that, but -80 degrees is the minimum, to make sure that the sample's chemical composition is maintained. Otherwise, we have seen that if we don't do that, and if we leave the sample a few hours just at room temperature, the infrared fingerprint of the sample is already changing substantially. So which also shows that the method is quite sensitive.
So let me ask a follow-up question. How expensive is the machine, you think, that you?
Well, the machine is, of course, right now almost
unaffordable.
Almost unaffordable, of course, because it is the result of I don't know how many years of development. But I would guess that this machine probably one day can be built for about $1 million of dollars. So, if you consider that it can have a throughput of eventually, if we have a automated sample delivery of a couple of 1,000 samples per week, per working week, then this means that about 100,000 samples per year. And if we write off this instrument over 5 years, then this is 500,000 measurements over the lifetime of the instrument. So you should just divide the 1 million by 500,000, and that's probably roughly from the instrument side the cost for the measurement. So it's I think potentially it's more than affordable.
All right.
Thanks, Ferenc, for the very nice talk. I have a question about the molecular printing. So you see a difference between the blood content for stage 1, 2, and 3, and 4. So what is the physical processes that you're probing or observing here? Is it just the molecules?
Thank you very much. Obviously, thank you. So the question is whether we see differences between different stages, and the answer is a clear yes. Basically, which actually manifests here in the differing effect size. This effect size is just basically the amplitude of the magnitude of this up and down regulation, sort of the half cycle gap. We'd refer to the spread of the controls. That's what is plotted up there as an effect size and averaged over all markers, right? So as you see, this shows distinct differences, and this is not just in magnitude. I don't have the plots here for you, but you should just believe me that there is also some deviation in the distribution of the markers. So obviously, these fingerprints corroborates what oncologists have been knowing for a long time, that different stages of even the same cancer are almost different diseases. The tumor changes whilst progressing. The tumor changes all the time as it's progressing. Our infrared fingerprints do reflect this well-known fact very nicely.
All right, there's a question on the other side. So thank you, Matthias.
A very interesting study. So I have a question about the sensitivity in terms of the blood volume. What is the limit for the sample?
Right now, we need 50 microliter for the measurement. So it's a slightly bigger drop of blood.
Thank you.
That's it, but probably this will become smaller as the technology develops. Eventually, probably a few microliters on the longer run. Yeah.
Fantastic.
So
Thank you.
it's really a very, very small amount.
Are there more questions in the room?
Thank you so much for the talk. I absolutely love the animations. I was actually curious, how did you convert the theory so well into visuals that we can understand?
I have to just delegate this. Thank you.
You have a question?
Sorry, hello. Just asking about Atoll World. I was confused because underneath most of the headshots were physical places, and then I didn't understand what Atoll World was. Understand it's a world you've created. Or I assume I just looked on my phone. Is the goal?
So you visited our website and you didn't understand
Just,
what is it about?
No, then I understood what it was. Before, I don't know what Atoll
okay.
World was. I thought it was an alternative dimension.
Okay.
But just really quickly, speaking on behalf of the state of Bavaria, where you're now visiting from, what is the role of the public sector, or perhaps, I see you've given a really colorful illustration of what it can actually do in the hands of those, whether it's cancer research or oncological research. What do you foresee? What do you think could be some applications of this research in the forthcoming decades? With the right sort of funding and public support.
Well, you know the famous saying that what is particularly hard to predict is the future. Well, I very much hope that this turns out to be a real application, and that's what we actually really fully focus on. And meanwhile, more than 80% of the resources of all my groups at MPQ, at LMU, and meanwhile in Hungary at CMF are channeled into this focus. It's incredibly challenging because it's not just laser science. It's to the same extent life science medicine, and to the same extent data science, because artificial intelligence is a massive component here to train the algorithm to find better and better ways. And we even think of how artificial intelligence could possibly use to actually artificially reduce the spread. Because at first sight, this within person variability of the fingerprints or any other set of health data is the ultimate noise limit, right? Biological noise limit, that, I mean, what you have to deal with, right? Just your own fluctuations over time, right? One would think. But we now have the chance with this cohort in Hungary with the 15,000 people, and from whom we now capture an increasing number of fingerprints, to try to discover some regularities within the within person variations. If we could train an artificial intelligence to recognize regularities within this seemingly nothing else but noise, then potentially we could further effectively virtually reduce the personalized baseline, which would mean that diseases which deliver just a small signal could be recognized earlier, right? So therefore, three major areas: laser science, life science, data science have to come together here. This is our focus, and that's what we believe in. But as I just touched upon, I do see that or I do believe and hope that that attosecond technology also offers quite some chances for actually advancing at least conventional electronic signal processing.
Thank you very much for your answers, Ferenc. So we had a few questions online, but I think you answered actually most of them in this discussion. So, and we're quite advanced already in time. So I ask everyone that still has a question, we will stick around for a few more minutes. So by all means, you can approach the speaker. Thank you, Ferenc, very much. This was an excellent talk as usual.
Thank you. Thank you.
Thank you for coming out.